get the recording going. And there we go. The big picture of where we were last time. So I don't know how far we're going to get today. I'm going to have to make a game time decision when class is over as to whether or not I think we have enough left for a full other class, or whether I just need to make a little video to finish whatever is not finished yet. So I will make that decision once I see how far that we are. If it ends up being that we need another class, then I'm going to have to push back the deadline for homework 1 2 more days so that you have at least a full week after we finish the material to work on it. But I figured that would be a good place to start. Does anyone have homework 1 questions yet? I have it pulled up, if so.
So I just realized that you gave us a starter, like a sample on the Excel spreadsheet. Is that right? In the data for last week?
I don't
You
have
did
a,
it.
no, I did
Oh,
not. The idea would be to, if you wanted to make a spreadsheet to make it easier to do, which I highly recommend, would be to make columns for what the -2 log likelihood that I gave you, a column for how many parameters are in the model for the means, another
mhm.
column for how many parameters are in the model for the variance, and then there would be 4 columns by which you would compute AIC and BIC under ML, which uses all the parameters in the total model, versus AIC and BIC in REML, which only uses the parameters in the model for the variance.
Okay.
Was that a lot?
Yes. Okay, so we have a column for the -2 LL. Okay, then a column for parameters for um, the
The means model, yes.
means model, one for the variance, the model for the variance, and then 4 columns. That's where I lost you.
4 columns by which you would compute AIC and BIC under ML versus REML, and the formulas for that are on here on slide 7. So AIC is the -2 log likelihood value plus 2 times the number of parameters, whereas BIC is -2 log likelihood plus the log of the level 2 sample size times the number of parameters. And so I gave you sample size, I gave you -2 log likelihood, and a set number of occasions that would then determine what the number of parameters are in each model. And so then this part down here distinguishes how you would compute AIC and BIC under each estimator. Under ML, all the parameters count, and under REML, it's only the column for the model for the variance, which is why I suggested 2 columns. And so this, like, the calculations here are relatively straightforward. This is a vocabulary exercise. That is what I intended. So like if I say saturated means, I want you to think in your head, okay, how many occasions? If I have 6 occasions, that's 6 fixed effects, because I have 1 intercept and 5 mean differences. And if I say unstructured variance, I want you to think in your head, okay, how many occasions do I have? And the formula for that is, it's in lecture 3, but it's n times n plus 1 over 2. And so for all of the models, you should know based on how it is described how many parameters are on each side. So mean side at this point is either empty or saturated. So either 1 if it's empty, which is just a fixed intercept, or as many occasions if it's saturated. The variance models are the ones that we're going through right now in terms of how many parameters are in each of those. Okay, does that help?
It helps.
It
I'll watch
helps.
the video.
Okay.
And I've never taken a vocabulary quiz quite like this, something that might include Excel. So usually it's like definitions.
Yeah, it's applying the definitions and using them in a I'll call it a relatively simple calculation. Like this is just adding things together. So mapping vocabulary onto what kind of model it says you're using and how many parameters that model takes. That's the idea. We have questions in the chat window. How would we know what is a better fitting model for the first question in section 1? The better fitting model is the one that has the smaller -2 log likelihood. Smaller is better in -2 log likelihood land, and we do significance tests to compare the fit of alternative models if they're nested. The difference between -2 log likelihoods is a chi-square. And so then you can use the chi-square test distribution to do that. And so that's something we'll get more practice with today. All right. Other questions on homework or stuff from last time?
I have a question about stuff from last time. I don't know if anyone else has homework though.
Go for it.
Okay. I'm trying to trying to conceptualize in my head like what we did with the different variance structures. And would it be fair to say that the different types of matrices represent different maybe like assumptions that you're making about the relationship between the occasions? Like,
yes.
Okay. In terms of like, okay, that's all then. Okay, I'm glad.
Yeah, no, that's a great way to describe it. So I had a question, I think from one of you in office hours, and I was going to bring up this point. This process of trying to figure out like what the right matrix is for the model for the variance is a very different thing than you would typically encounter in building models for the purposes of prediction. So if you think about just going back to like a single level regression model, right? Like we would have done in intermediate statistics or in 6242 or correlation regression, one of those or like single level classes. We usually paid attention to what goes into the model in terms of predictors and how effective those predictors are at capturing the outcome. So we would look at how much variance in the outcome has been reduced, measures of R-square, and the significance of the predictors and that kind of thing. That is a different set of tasks than what I'm talking about. This process is not about explaining variance. It is about making sure the model has accurately captured how much there is and how much covariance there is. And I thought of another real world sort of example that might help to make that distinction. So once upon a time, I used to watch on CNBC, there was a show that was hosted by Susie Orman. Do you know who this person is? A few people do. Okay, for those of you who have not seen Susie Orman, she is a financial expert who like got on the Oprah Winfrey show a few times, and her career took off and she got her own show, and she is an investment specialist, and she had a show about money on CNBC where people would call in and ask for advice, what they would do in various situations. And there was a segment like, can I afford this? Where they would describe like, well, how much money do you make in a year, and what are your expenses, and how much do you have saved, and she would make a decision as to whether they could afford things. And usually the show made me feel a lot better about my situation in life because I didn't have like $200,000 in credit card debt, and I wasn't asking if I could buy a boat. You know, I was doing relatively well than compared to the people on the show. But she also helped tackle people who were in serious debt and try to get them situated in terms of how they would go about addressing the problem. And step number one for the people who knew they were in serious debt was to figure out how bad it was, to actually open the bills that they had shoved in a drawer and tried to forget about, and find out just where they stood in terms of how much they owed on credit card A and credit card B and medical bills and student loans and all the sources of debt that you might have. So that's step one, is to figure out what do you even owe and to whom. Step two then is to make a payment plan as to which debts should have priority. You pay down the ones that have the highest interest rates, and then you work your way down to the ones with the lower interest rates in most cases. So if I were to map on that kind of money management advice to this situation, figuring out what kind of variance structure we have, whether it's autoregressive or Topolitz or whether it has to be unstructured, that's like figuring out how much debt you have in the first place. That's the process of opening the envelope to see what's what. Then once you figure out what your debt structure looks like, see what I did there? Debt structure of the matrix. Then you can go into the payment plan where you try to reduce that variance by putting in predictors. So we're just trying to figure out what's there to begin with. And it's not just about how much variance there is. It's really more about what kind of covariance there is. What are the sources of covariance that happen because we're sampling people repeatedly? And what are the sources of covariance that happen because of the spacing of the occasions? Because occasions that are closer together in time are often more related. So we're trying to tackle just what is there before we go and then put predictors in to capture variation that is actually predicted in that case. So I don't know if that helps at all, but this is a process that you don't normally have to go through in a lot of areas of statistics. It shows up in the context of multivariate data. So when you have the same unit measured repeatedly as a general concept, that happens in longitudinal data. That also is the way of looking at clustered data. So if I have multiple schools and multiple students from multiple schools, you can think of the school as the unit that's being measured repeatedly by different students. And it's a multivariate correlation dependency problem, the same type of thing that we're doing here. So the strategies you would use to address it are different in longitudinal data, but it's the same process of figuring out how much variance and covariance do you have and what kinds are they, and then you can build your model to try and predict it away. Okay, I can tell the caffeine has kicked in here. Another side benefit to not having the microphone is that I can drink my soda freely. Any questions, other questions, or clarifications I can help with? All right, then big picture, the example that I have to follow. We're going to look at alternatives that fall in the middle of this complexity continuum in describing the model for the variance. So we are focused for this unit on fluctuation data. This is slide 2 of lecture 4, where time is not a prominent factor in terms of systematic change. We wouldn't expect people to increase or decrease. We would just expect some sort of variation across time. And so our focus is going to be on the model for the variance, not the model for the means in this case. And we're looking for something in between here. So the simplest structure that would ever apply to longitudinal data would probably look like this, compound symmetry, where we would say that there is person intercept variance at level 2, within person fluctuation variance at level 1, and that those two things together are what make the total variability. The total variability is the same across time, so the diagonal is the same, and the total covariability is the same across time too, as given by the intercept. So no matter how many occasions we have, this is a 2-parameter model for the variance, compound symmetry, otherwise known as random intercept only. Over here is as many parameters as we could possibly need, unstructured. Every occasion gets its own variance, every pair of occasion gets its own covariance. It's n times n plus 1 divided by 2. So if I have 4 occasions, that's 10 parameters. If I have 5 occasions, that's 15. If I have 6 occasions, that's 21. So it gets big quickly. So our goal is to try and come up with something in the middle that fits as well as unstructured, but doesn't take as many parameters to do so. So that's what we're going to do. So rather than go back through the slides, I wanted to go straight to the example that goes with these data, because I think seeing numbers helps to make things a little bit more concrete in a way that abstract notation sometimes does not. So this is example 4. I figured out how to make Word not show all of the header stuff, so I've got more room on my screen here. These are real data. These are not from the textbook, and so this example does not have the data in the data files. It has just the syntax and output. These are data that come from a friend of mine, so this is a true story. When I was a graduate student at the University of Kansas, I worked with a clinical graduate student. She is the creator of the Heartland Forgiveness Scale. I've talked about that in my other class. My #1 cited publication with a bullet, by the way, is my participation in helping to build this scale when I was in graduate school. So don't ever think that what you're doing now doesn't matter. It's by a far margin my most cited publication. This was from her dissertation data. So she went in to propose a dissertation, which was pitched as a cross-sectional study. She was going to examine psoriasis severity and give psoriasis treated patients, her husband is a dermatologist, that is not a coincidence, She was going to select a sample of patients from the clinic where he worked, give them various measures of coping and personality, and she was going to look at the extent to which the relationship between stress and psoriasis severity was attenuated in people who had higher levels of forgiveness and better coping mechanisms. That was going to be her dissertation. She took that plan to her proposal meeting, and she walked out of her dissertation proposal defense with a longitudinal study that her committee had designed for her. They wanted her to look at psoriasis and stress flare-ups. The idea that even though you have a disease, that disease doesn't constantly express itself. Sometimes are worse than others. And so they wanted, for her to look at the within-person relationship between relative increases in stress and how that predicted subsequent flare-ups in their psoriasis. So she did it. So she added this extra part of her dissertation. She collected data for 8 weeks. I helped mail out all the packets and enter all the data as my work on part of her project. And this is what we got. So this picture right here is what's known as a spaghetti plot, colloquially, because it's what, if you took like a handful of colored spaghetti and just like threw it at the wall, that's what you would get. By the way, in a paper, this is a plot of individual trajectories. This is not a spaghetti plot. But the black line here is the mean for the sample. And the point of me adding the black line here that's buried under all the colored lines is that the mean doesn't change over time. This is not a treatment study. This is just, we asked people for 8 weeks, hey, how's your psoriasis this week? And they filled out a questionnaire and, oh, how was your stress this week? What happened to you? And we observed those responses. Later in the semester, I'm going to show you what actually happened in terms of stress predicting subsequent psoriasis flare-ups, which is why we are only using weeks 2 through 8, because week 1 was discarded because we're interested in a lagged effect. So the point of this exercise is just figuring out for these 7 observations within a person what the structure of variance and covariance looks like in this psoriasis measure. So this is an outcome of psoriasis severity, where higher scores mean a worse condition at that occasion. So this is the story. It's real data. It means it's necessarily messy, and I don't know what the right answer is. Okay. So first off, because I have balanced data, so each person turned in a survey once a week. It was close enough that we were able to say this is time 2, this is time 3, this is time 4, and we can actually estimate what I would refer to in the book as the answer key. So this is an empty means model. So there are no predictors with respect to time. So only a fixed intercept in this model, because I don't need time as a fixed effect. There is no change over time. So I don't need a different mean at each occasion if the means aren't changing. So a fixed intercept is what I'm doing throughout this entire set of examples. We are focusing entirely on the model for the variance. So the answer key model, and this is the part that I didn't do explicitly in example 3b, but I knew this was coming, so that's okay, is type equals UN. So unstructured is every occasion gets its own variance, every pair of occasion gets its own covariance, and in SAS, I am asking for that structure. I am also asking it to show me what that structure looks like. So the letters R and R core are asking it to print the R matrix that is predicted by this model and the correlation version of that R matrix. So R is going to be variances and covariances. If you standardize that, R core is the correlation standardized version. And I am also saving the results of the fit statistics. So ODS output in SAS is a way to take the tables of output that you get and save them as SAS data sets. So this is necessary if you want to use the macro program that I wrote to do likelihood ratio tests for you. So I'm using that so that we can get the program to do all of the math for us. If that's not something that you like, I want to point out this resource, which is available online with the data files. This is an Excel sheet in which I have tabled all of the models that we're going to look at, and I have computed likelihood ratio tests for various combinations of the models. And so this right here, I don't know if you can see this very well, this p-value column, it's a chi-dist function. So this is how you can get an exact p-value that corresponds to the difference in -2 log likelihoods between models. You can do it in Excel. So this is the routine that I had programmed into SAS as a macro. Stata has a routine for this, it's called LR test, and R has a routine for this that's called ANOVA. So you can use Excel if you want to, or you can use my little macro program, and it takes as input the data sets that contain the fit statistics across models. So that's what's being saved here. And Stata right here is unstructured. So the structure of Stata we had talked about before, but just to remind you, the outcome is listed first. It would normally be followed by predictors, but we don't have any because this is an empty model. Stata automatically puts in a random intercept, which I want shut off because all of my variances and covariances are in the R matrix for this model. And I am asking for an unstructured matrix using week as my index for level 1 time. So week is being used as an ID variable. That way, if there's any missing data, then I know which week a given observation came from and which row in the R matrix it should contribute to. And I am storing the fit statistics from this model with an estimates store option, and I am naming that piece of output that I am saving fit UN for fit for the unstructured model, which is the same name that I gave it in SAS. Okay, let me pause for a moment. Questions on syntax or concepts?
What's the N124 for the E-stat?
So in Stata, it by default computes BIC differently than what happens in SAS. And so I am adding the N option to tell it what the N should be in the BIC formula. So just to recall, this is slide 7 where the formula is. BIC has log N as part of it. And different programs interpret what N means differently. Some programs think that N is number of people. Some programs think that it's total number of observations. I don't remember what Stata does by default, but I remember learning that it is not what SAS does and how to fix it. So I have manually put in the sample size that I want it to use in creating IC, that's information criteria. So AIC and BIC are two specific flavors of information criteria. And thank you for pointing that out. We haven't done these ones yet. SStat is a way of asking for output from the run of the model that's not given by default. And W correlation with an option for comma covariance is Stata for I'd like the R matrix printed, please. W correlation stands for within correlation. And if you just want the R core correlation matrix, that's the same thing without the option for covariance. So these are helpful to be able to visualize what your model has actually said the structure of your variances and covariances should look like. Otherwise, it just shows up in a giant table of listed parameters that aren't organized in like a matrix form, and it makes it harder to see them and follow them. Okay, other questions on SAS or Stata? All right, R people, your version of type equals UN is all of that. So it's core sim and then telling it to do it as a function of week as numeric. By the way, it made me make a new version of week that started at 1 instead of 2. That was an error that it threw, so whatever. And then it's organized by subject ID. And then this second part here, weights, is a way to allow heterogeneous variances. So in Stata, it's it's two separate commands for what the correlation structure looks like and then whether or not the variances are heterogeneous or homogeneous. And so the weights part gets you heterogeneous variances across time. The core sim part gets you all possible correlations between all pairs as a separate parameter. So this whole thing together is unstructured. And then I'm asking it to get printed and to show you what the matrix actually looks like that's implied by the model. Okay, so I know that's a brief overview, but this is the only part that I think is new for this command. Any questions from the R folks in the crowd? No. All right, then here's what we end up with. So SAS output I have truncated somewhat because it's voluminous, but this model, unstructured, has 28 parameters in the model for the variance. So that is because I have 7 occasions. So n is 7 times n plus 1 divided by 2. That gives me the 28. So here's the little formula up here that gives you that. So 28 is a lot. So what I'm looking for is to see, okay, if I just let everything be what it wants, what does the pattern look like? And can I approximate that with something that's simpler? It thinks I have 124 subjects, which I do. That's how many people we have data from, and that each subject has up to 7 observations. So here is the answer key, highlighted in blue, where this is the R matrix to start with. So on the diagonal are variances, and on the off diagonal are covariances. Because covariances are scaled in terms of the variances of the variables that they're referring to, it can be easier to look at correlations to describe the associations. So if we just look at the diagonal here, do these variances look the same over time or not the same? I'm just eyeball it. Some of them look the same, some of them not, right? Like, I don't know what's up at week 1. There's less variability there than the others, but most of them are around like 0.8. So we only have 2 options, unfortunately, in these sets of models. Either the variances are treated as all the same, which is a homogeneous structure, or all different, which is heterogeneous. So it's unclear, just from eyeballing it, if there's different enough to need the heterogeneous structure. What about the correlations? So I've bolded those in the off diagonals here. There. Same over time or not the same over time? Pretty high. So between week 2 and week 7, for instance, there's still a correlation of 0.8, but it does look like, with a great deal of inconsistency, but the correlations for occasions that are closer together are like a little higher. They're closer to 0.9, whereas some of the others are 0.8. So what we're seeing in this correlation matrix is a great deal of person dependency. Regardless of how far apart in time the observations are, there is a very strong correlation. So the question will be, what else are we going to need besides just that idea? So the R matrix structures that I'm going to show you with to start with don't capitalize on the fact that we have this strong person dependency. That's why they tend to be less useful. These are the ones that I told you are more legacy in terms of I want you to be familiar with them, but they tend to be less useful, particularly for this type of data where there's a strong correlation throughout. But this is the answer key. So given that this is going to fit best, given -2 log likelihood, our goal is to find something that approximates this pattern with fewer parameters. That's what we're trying to do. Okay, so questions before we look at our alternatives? Okay, well, the simplest one. What if we just did compound symmetry? Is that good enough? So compound symmetry, type equals CS. We had seen that one before. That's otherwise known as the univariate approach to repeated measures ANOVA. That is exchangeable in Stata. And core comp sim in R. One additional piece of output here this is something that is specific to my example. So fit test, this %sign fit test, this refers to a little program that I wrote that is included in the output or the syntax files for this example that simply takes the output from one model given by this table right here, the information criteria table. It saves that table as a data set. And then the other table that you want to compare the fit to gets saved into the same data set, and they get stacked on top of each other. And then I calculate the difference in -2 log likelihood. So to use this little macro, it only has to take 2 pieces of information. I want to know which of the data sets has the model results from the model with fewer parameters and which one has the model that should have more. So fit CS is the name of the table that has the fit statistics from the compound symmetry model, so it's being saved right here. Whereas fit UN was the same table that had been saved up above for the unstructured model. So if you want to use my macro in SAS, you just have to add this line of code to save the results from the model that you want to be used in the comparison, and then refer to that inside this command. So the %sign fit test invokes the program that I wrote using these 2 pieces of information as part of it. Likewise, in Stata, estimate store saves the information from the compound symmetry model as fit CS, and then LR tests does the likelihood ratio test to compare their fit, where it wants the one with more parameters first, by the way, and then fewer goes second. And so I have a note here in terms of the comment. What I am asking with this likelihood ratio test is whether or not compound symmetry fits significantly worse. So if I have a model with 28 parameters where everything gets to be what it wants, can I approximate that with only 2? Or is it going to fit worse? That's what I want to know. What do you think is going to happen? Do you think 2 is going to be enough? It'd be a very boring example if it were. Let's put it that way. All right, and then ANOVA with the 2 model results in R is how we do a likelihood ratio test. So I had saved UN as the analysis for unstructured. Then I saved the results of this one as CS, and then the ANOVA command at the end here does the likelihood ratio test in R. So here are my results. First off, this is my model predicted R matrix. So this is not the data. This is what the model says the data should look like. So this prediction of what the data should look like says that the variance is the same across time. That's why these numbers are all the same. The model also says that the covariance across time is all the same. And so that's why these numbers are all the same here. And if I convert the covariance across time to a correlation, that's shown in the R-core matrix. And so this is my intraclass correlation. So I did the math for you to show where it came up with that. It is the proportion of variance that is due to random intercept between person differences. Right here is that parameter, the 0.68, relative to the total, which also includes the residual variance at level 1. So the way to think about this output is that what is contained in the model for the variance is going to be right there. Each specific parameter that's being estimated is going to be listed in that table. How those parameters get reconfigured to make the prediction is illustrated in the R matrix and in the R core matrix. And so where this 0.8127 comes from is that's the total that you get if you add the between person compound symmetry part to the within person residual part. So those two numbers compute the total. The predicted covariance across time is just that number. And if you standardize that number, you get to the R correlation right there. That's the intraclass correlation. Okay. All right. Lane, did you have a question?
No.
No? Okay. Anyone else have questions? Okay. So this model has two parameters. It says the variance is the same across time, and so is the covariance, and so is the correlation. So the output that we get is not going to answer the question directly as to whether or not this is good enough. This is the only thing that SAS provides without extra work. This likelihood ratio test right here, what that is testing is whether or not we need the random intercept. So that's testing the significance of the intraclass correlation. And yes, it looks like we do. A correlation of occasions from the same person of 0.84 is not 0. Now let me think about what to do with this number in practical terms. What does an intraclass correlation tell you? Two ways of defining it. I've said them both, but I'm looking for you to recall. Intraclass correlation tells you what?
How dependent one point is with another.
The average correlation of occasions from the same person. Yep, the extent of dependency. What if I wanted to talk about it as a proportion of variance? Level 2, yeah, 84% of the total variability in psoriasis outcomes is between persons, is level 2, is due to the random intercept. This is vocabulary, is cross-sectional, is because some people have worse psoriasis than others, period. Now, why would I make that point in reference to my poor friend whose dissertation committee insisted that she do this? 84% of the variability is cross-sectional. So this is an 84% waste of time. She wanted to do a cross-sectional study, and they were like, no, you have to do the longitudinal study. And she did, and she found out that it's a cross-sectional study. So all of that work to collect 8 observations from each person, and only 16% of it is new information. So some people have worse psoriasis, period. That's 84% of the variability right there. Some occasions are worse than others is the remaining 16. So that means that if I were to use this information to foreshadow what kind of predictors are going to be useful, what kind of predictors are going to be best suited for this data set? Did she scream? No, because we didn't know how to do any of this when I didn't know any of this as a graduate student. I don't even remember what she actually did to analyze these data. We probably just took the mean across time or something, because that's what we knew how to do when we were in grad school. I lost my thought.
Lisa, can I ask you a question?
Yes, I got it back. Go ahead.
Yeah, so like a thing, 16%, like only 16% is from level 1, like a time differences. What would be a good, kind of cutoff point to like in decide if it's like a more cross-sectional study or a more longitudinal study? Because in like a regular multi-level modeling, like often ICC, like a cutoff point of ICC to use multi-level or single level, it's like a kind of 5%, right? I think it's not gold standard, but it's what I often hear. So in the case of like this kind of data set, yes, 16% is not big, but at the same time, it's not very small. So like, how would you like define like, oh, it's more cross-sectional data, or like it should be more longitudinal data set? Like, how would you decide that?
As long as it's not a correlation of one play ball. 16% is not nothing. And actually, we did find a lag 1 relationship that if you have a worse week than usual in terms of your stress, that shows up in your skin a week later. We actually did find a significant relationship. It's not huge, but it was there. So there isn't a cutoff for how much is too much. It's just that if I know that 84% of the variability is because some people have worse disease severity than others, the only way to explain that is person characteristics. Like what makes people different from each other is 84% of the action. What makes some weeks worse than others is 16%. So the whole purpose of doing this study, though, was the latter. What makes some weeks worse than others was the reason they wanted to do this. So yeah, this is one of those things I had no idea what to do with the data. None whatsoever, because it wasn't a growth model. So I learned about growth modeling. I'm like, but it doesn't grow. Like, what do I do with this? And so I took it to, by the time I graduated and I started a postdoc at Penn State, they had something called Methods Lunch, which was literally like all the methodologists on campus that were from human development and family studies, which is where I was, and gerontology, and some folks from education sat around and ate lunch, and people would sign up to bring problems to them, and you would get advice. And so I brought this problem, and I'm like, it's longitudinal, but it's not growing, and I don't know what to do with it. And they're just like, do the growth model without time in it. You can do that? Yeah. So, and then the whole thing was born. So that was actually part of the reason that I titled my book Modeling with In-Person Change and Fluctuation, because I didn't even know that was a thing until far too long. So that wasn't in the dissertation, but it did end up actually working out to be a finding. So anyway, the 16% novelty of the study did actually bear fruit. By the way, Shinji, the rule about when an intraclass correlation is small enough that you can ignore it, only when it's 0. Doesn't matter how small it is, because the design effect that it creates is a function of level 1 sample size, the number of observations per level 2 unit. And if you have enough of those, you can end up with bias, even if you have an intraclass correlation of 0.01. So only 0 is the only time you can ignore it.
So the 16% explains the, like if I have one bad week over another, I got my more stressful events. So it's explaining my person to person or instance to instance difference within the same person.
Mm-hmm.
Okay, thank you.
And in this case, the outcome is psoriasis.
Mm-hmm.
So it's within person variation across weeks in how bad they said that their psoriasis is currently acting up. So it's literally like a stick figure person, and they color like how much of the stick figure has problems, and then we compute like a proportion of body that is affected. It's like that kind of level of measure. It's log transform because it was skewed, so that's why the numbers are sort of weird.
Okay, thank you.
But yeah, thanks for the question.
So maybe it would have been different if they had a longer time period that they were observing, where there was more variation across time.
Yes, it is entirely possible, but she needed to graduate, and so we did it for 8 weeks in the summer, and that was the reason why. So there's always a reason, right? We can pretend that it was theoretically motivated in terms of the time flag, but no, it's pragmatic. But anyway, oh goodness, good times. I still remember stuffing the packets every week to mail out to people, right? Yeah, so anywho, is this good enough is the question, and most of you guessed probably not, and those of you who guessed probably not are correct. So this is the output that my macro program provides. So it has the fit of the model with fewer parameters on the first line, the fit of the model with more parameters on the second line, and then I added these 3 columns out here. So div-diff means the difference in the -2 log likelihoods. You can't name a variable with a minus sign and a number to start with, and so I had to use deviance, which is a synonym for this in this literature. So 156 is the difference in -2 log likelihood between these models. And that difference is compared to a reference of degrees of freedom for the difference in the model parameters 26. And the p-value is 0 to as many places as it would print. So what that means is that unstructured that has 26 more parameters fits significantly better by a considerable margin. So way out in the tail in terms of where the expected value would be for a chi-square. I think it's equal to degrees of freedom if memory serves. I think the expected value is the degrees of freedom in chi-square, so 26 is like what it would be if it were chance, and so 156 is a lot. So yeah, this is not good enough. So unstructured was the sweatpants, compound symmetry was the skinny jeans. And I realized after class that some of my examples might be accidentally misconstrued. I'm not talking about any sort of body shaming bullshit, any of that, right? There is nothing wrong with anyone's body. There is everything wrong with certain kinds of pants, though. The problem is the pants, right? And the same can be said. All data are beautiful. All data should be celebrated. It's the fit of the model that can be the problem. And if your model don't fit, get a new one. If your pants don't fit, get some new ones. Everybody should look good and feel comfortable in their pants as their God-given right. That's what I believe. And that is why I am not going to be sad. I should say the other way. I will be very sad when I have to start wearing work clothes again. That will be, a tough transition. But maybe work clothes will look different post-pandemic. Maybe pajamas will be acceptable day wear. Even if you go to the office. Anywho, so as another potential fit, AR1. So this is my tapered jeans analogy. And so to fit an autoregressive structure as an option, it's type AR with a 1 in parentheses in SAS. It is AR1 without parentheses in Stata. And it is core R1 in R as a built-in correlation structure. And I have a note that if you have unbalanced occasions, this is the only one that you can actually still use if you switch out the type. So if I didn't have equidistant weeks, if I had occasions that were unequal, then if I typed SPPOW week, that's a spatial power structure in SAS. I can have unbalanced occasions and still have an AR1. And in R, it's the letter C. So core CAR1 is the same thing. So this is the one exception in terms of being able to address unequal interval data. You can do it if you have those options. So here's what the model, the AR1 model says our data should look like. So in terms of the variances, this is a homogeneous variance structure, so it still predicts the same variance at each occasion. However, it does not do so by saying how much is level 2 and how much is level 1. It's just one number. It doesn't care because it doesn't use the concept of a random intercept to predict the correlation between the occasions. It uses R for that instead. And so it's easier to see how this works if you look at the R correlation matrix. So the two parameters in the model, one of them is what's labeled as residual, which is actually the total variance. And the other parameter in the model is the AR1 correlation parameter. So you can see that play out if we look at this R-core table. So the correlation between the first two occasions, 2 and 3, 3 and 4, 4 and 5, that whole off diagonal is the same. Because this model says that any correlation between occasions 1 unit in time apart is R. So R was estimated at 0.8955, and so that's what it predicts for pairwise occasions, adjacent occasions. Then occasions that are 2 units in time apart are correlated at R squared. And occasions 3 units apart are R cubed, and 4 units apart are R fourthed, quadrupled, whatever we decided on last time, R to the 4th, R to the 5th, and R to the 6th. So we get this whole pattern of changing correlations over time out of one number. So it's a relatively parsimonious structure because it's only 2 parameters, the same as compound symmetry. It's not nested in compound symmetry because it's a different two parameters, but it is still nested in unstructured. So how do you think this predicted correlation matrix compares to the right answer? Do you remember what it used to look like in unstructured? No? You don't have the correlation matrix memorized yet? Here it is. This is the right answer. This is what you get when you estimate everything separately. I want to point out the lowest one down here. The highest lag between the first occasion and the seventh occasion is still a correlation of 0.8. Whereas the autoregressive model predicts that same correlation to be only 0.5. So much like tapered pants that narrow too much from your waist down to your ankle and are unflattering on nearly everyone, this AR1 matrix narrows too much. It predicts a correlation that decays exponentially across time, which is a bad fit for this particular data set where the correlation remains pretty strong even for distant occasions. So for that reason, as we might have anticipated, it does not fit as well as unstructured either. So a difference of 28 parameters, difference in -2 log likelihood of 97, and a p-value that is 0 out to 10 decimal places. So that doesn't fit very well either. Okay, questions? Next one then. This one is not available in R as a structure that I could find. I searched for too long to try and find it and eventually gave up. So it's possible that it's out there and I didn't find it on the Google, but that just means that it's probably not as readily available as the others. But Topolitz, Top 7, or Topolitz 6 in Stata. So Topolitz, that structure, just to review what that one looked like. Let me find it again. This one right here, it's in slide 13. The idea of a Topolitz matrix is that occasions that are the same distance and time apart have a shared covariance, but each distance gets its own. So there's one covariance estimated for 1 unit apart, another one estimated for 2 units apart, another one for 3 units apart, and they're not functions of each other. So it's not like squared and cubed, they're separate numbers. And so what a Topolitz 7 means in this case is that we have a relationship all the way through the matrix. So the highest one is with the first occasion and the 7th occasion, so that's lag 6. So there's 6 possible relationships being estimated, and then the 7th is because in SAS it counts the diagonal. So there's 7 parameters total because I have 7 occasions. Stata, just because, I don't know, just to mess with you, it doesn't count the diagonal. So that's why Stata calls it Topolitz 6 instead of 7. But it's the same idea either way. And so here is what it says. It also has one total variance. It does not try to separate between and within. It's just all put together because it models the correlation with these lagged things here. So like that 0.72, that's the predicted covariance between occasions 1 unit apart. And then here's the other one for occasions 2 units apart, and then 3 units apart, and so forth. And that translates into these correlations down here. And so because I want you guys to like me, I've labeled all this shit for you. So it's impossible to tell what it is. It took me a very long time to figure this out, and I didn't want any of you to work that hard. So when you have a model in which the variances are homogeneous, the Topolitz is phrased in terms of covariances. And so that's what these parameters are that it labels Top 2, Top 3, Top 4, and they show up in the R matrix up here. So if I just look at this pattern, this one looks pretty good. It's doing a pretty good job of capturing the idea that the correlations that were closer in time are higher. They were around 0.9, and it decays a little bit, but not much. So let's see how it turned out. Dun dun. P of 0.047. Ugh. Now, why do I say like that? Why am I displeased with a significant p-value?
That means there's a significant difference between the two models. So
Yeah.
unstructured still fits better.
Unstructured still fits better by this much. Yeah. So even though I've saved a bunch of parameters, it looks like it's still not quite where I would want it to be. So yeah, my model with the Topolit structure fits significantly worse. That's what it's saying. So what about the variances? Well, my model said that all 7 variances are supposed to be the same number. What if they need to be different? Okay, I'll do that. Only in SAS. That's the only program I could find a Topolit's heterogeneous structure in. So the key is the H. Adding the H to any structure in SAS gets you a version that has different variances over time. And so then each occasion now has a different total variance according to the model. So relative to the previous model, how many parameters did I have to add to pull this off? Topolit's 7 versus Topolich H7. In letting all of the occasions have a different total variance, how many more parameters does that take? Got to vote for 6. Anyone else want to chime in? 6 sounds good. N-1 more generally, but yeah. Because I have either 7 or 1. I had 1 before, now I got 7. That's a change of 6. So I can ask 2 questions basically about this model. Did adding different variances for each occasion help? Like, am I heading in the right direction? And then, are we there yet? Did it help enough to get me into not worse than unstructured? And so once we have different variances across time, then the parameters of the Topolit's model are correlations instead, because covariances differ by variances, and so they phrase it in terms of correlations. So that's why I have labeled correlations down here instead of covariances. And here we go. First question, did adding 6 more variances help? That's what I've highlighted here. Is there a difference between the model that had 1 variance and the model that had 7? Yeah. P-value, not significant. So no, it actually didn't help. So whatever the problem was for a discrepancy between the Topolit's model and the unstructured model, it's not in the variances, because adding them to be different didn't help. And this model is now significantly worse than unstructured. So spending those extra 6 parameters did not help. So right now, I don't have anything that fits good enough. And if you read sort of most traditional versions of mixed effects models and longitudinal analysis, like in the statistics literature, like some of the older stuff, this would be the end of the story. Couldn't find one, wah wah, better stick with unstructured. And that is not the case. So there's a whole nother set of these models that incorporates a random intercept. So this idea that, yeah, people differ from each other, and the fact that people differ from each other on average creates covariance across time, no matter what time it is. Let's build that into the model. And then we'll see what else there is. That's the idea. of the G and R combined structures. So I want to show you then, turning back to the PowerPoints for a moment, this sort of idea. So slide 15 in lecture 4 is where we are. So the other type of alternative covariance structure models are ones that build in a random intercept. They do it in a different place. So this idea that no, we should always have a random intercept. Let's put that in as a default, and then we'll see what else is there in terms of the residual covariances. That's the idea that these models are based on. So to pull this off, we need to have some more letters. So adding to your vocabulary list, G. The G matrix is a new place, we haven't seen it yet, that is going to hold the random effect variances and covariances from our model. Right now we have one, just an intercept. So G is a matrix that holds one thing in it, a scalar. But it's separate. So R then is going to be only the within person matrix now. R has the level 1 residual variances and any covariances that are left over after pulling the random intercept out. But we can put them back together again to show the overall predicted marginal covariance matrix, and that gets a name V. So adding to your list, level 2, between person, mean differences due to a random intercept live in the G matrix. Level 1, within person, fluctuation over time, residual variance and covariance is what's left in R. And if you want to put them back together again, that's V. Those of you who are good with matrices, I am not among you, by the way, I'm jealous, but might be looking at this and going, yeah, how can you put them back together? They're not the same size. They thought of that. So they get put back together after sandwiching around the G matrix two other matrices to get it to the right dimensions. And so the ingredients, though, are going to look like this. So what if we took our compound symmetry R-only model and described it with this new language? So if I take the random intercept variance out, right? So this is what we're going to end up with. This is compound symmetry. If I pull the random intercept variance out and put it over here in G, then R that's left looks like this. So what this is making explicit is the idea that when you have a random intercept in the model, that already predicts covariance between occasions. The question is, do we have any other covariance amongst the level 1 residuals? Should these zeros be something else? And we have choices as to what they can be. They can be nothing. They can be zeros, which is like the VC structure. They can be AR1. They can be topolits. They can be lots of different things. But it's going to be a lot easier and a lot more parsimonious in most cases to predict the correlation among the residuals than to predict all the correlation in one set of parameters. So if you take this G matrix that has this random intercept here, level 2 between person mean differences, and just sort of like stick it everywhere over here, you end up with this result. So the combined compound symmetry form is going to be in a place called V. So the language is different, but the concept is the same. What we had just all this in one matrix before is getting pulled into pieces. That way we have more choices as to what we put in each one. We have G at level 2 and R at level 1. And here's how it actually works. So in order to get those things to be the same size such that they can be added together, you have to pre and post multiply the G matrix by a vector of ones, that is the number of occasions for this person. So that's how it actually happens, is this piece right here. So what we end up with is actually a V matrix for each person that depends on how many occasions that they have. People with more occasions can have a V matrix with more dimensions. So G is going to be the same for everybody. R is the same for everybody except with the dimensionality needed for that person's number of occasions. So that's how they actually get put back together again, is to create this form that's V, that's compound symmetry. So I know this is a very abstract sort of idea, but conceptually, the idea is, okay, so yeah, occasions from the same person are correlated. Great. Let's take that, stick it over here, and deal with what's left. That's the idea. In terms of pants, this approach is like going to a tailor. That was the other thing that I learned from What Not to Wear. Tailors are very important. So whenever I go shopping, which hasn't happened in a very long time, all I have to do is see whether or not a pair of pants is tailorable, rather than trying to fit them off the rack, because that's not going to happen. And so Stacy and Clinton always recommend fitting the hardest part of your body to fit, to make sure that the clothes cover that, and then you can nip and tuck and anything else. So like for me, my legs are actually wider than my hips. So getting pants past, like pulled up, if I get them pulled up, I win. Because from there, you can get the waist taken in, you can get the cuffs brought up if they're too long, you can get, if it's the wrong shape at the bottom, you can get it straightened, you can do all of those alterations. And so it's like, fit the part of your body that's the hardest first, set that aside, and then see what else needs to be done. Take the primary source of the correlation of occasions from the same persons, that random intercept, set it aside in G, and then see what's left in terms of the residuals, what else is needed. That's the logic of the model. How are we doing? Fun stuff, isn't it? Remember, this is the prep work that we're going through to make sure that your paint job looks good, right? This is the taping and the patching and all of that is boring and not interesting in terms of hypothesis testing, but it is necessary to get the predictor fixed effects down the road to be what they need to be. And in terms of my friend's dissertation, part of the example that I'm going to show you is that you actually end up with a non-significant result if you use the wrong covariance structure in her data. So the one finding that she had actually does depend on getting the right structure for this. So, all right, executive decision time. I think this is going to require another class, so I'm pushing homework back 2 days. So I will update the website and the due date. It will be due 2 days later after it originally was, which would be now March 3rd. That way you have at least a full week after we finish talking about this stuff to get it done. But you should be able to do at least half of it right now. So you can go ahead and get started and let me know if you need help. All right. Okay, any questions before we call it a day? Then I think that's enough for today. We'll talk about pants, money, fit, covariances next time. So have a good weekend. Thanks for coming. Take care of yourselves.